Welcome! Today we're doing Math Analysis, Chapter 5, Section 1, more on verifying identities. I'm your host, Dr. D. Okay, so this section is more on verifying trigonometric identities. That's not more on verifying trigonometric identities. Okay, so just as a review, the trig identities that we already know is sine theta equals 1 over cosecant theta. Now notice, just to simplify it, just to make it a little bit easier to write, I didn't put the angle here, so I just said sine is 1 over cosecant. Now that's not proper notation, but it'll fit our purposes for now. Then cosine and secant are reciprocals, tangent and cotangent are reciprocals, and so cosecant sine, secant cosine, cotangent tangent. Then we have our Pythagorean identities, which is sine squared plus cosine squared equals 1, and since it's plus, order doesn't matter. Now when we go to secant and tangent, it's minus, so order does matter, and the order is S comes before T in the alphabet. So secant squared minus tangent squared equals 1. And then when you put the cos on, it's the same order. Cosecant squared minus cotangent squared equals 1. Now the symmetry identities, remember, sine is symmetric with respect to the origin, which means it's an odd function, and that means sine of negative x equals negative sine of x. Cosine of negative x equals positive cosine of x. And tangent of negative x equals negative tangent of x. Now when we're verifying the trig identities, the page 213, that green box, really does a good job of explaining what you're allowed to do and what you're not allowed to do. So notice it says, as a general rule, work on only one side of the identity. We cannot assume the equation is true, so properties of equality cannot be applied. What that means that you can't multiply both sides by the same value, or you can't divide both sides by the same value. You can't add both sides, something to both sides, or subtract. Because basically it's not an equation, it's something we're trying to prove is an equation. Then number 2, work on the more complex side. So you're allowed to work on both sides and make them the same, or you could work on the complex side and make it equal to the simpler side. Number 3, if an expression contains more than one term, you can use algebraic principles such as a over b plus c over d equals AD plus BC over BD. So basically you can get common denominators and, and add fractions. Number 4, converting all functions to sine and cosine can be helpful. If you have a lot of secant and cosecant in there and tangent, cotangent, if you make everything into sine and cosine, then you could see things canceling. Then you're allowed to do all your algebraic skills, distributing, factoring, multiplying by a conjugate only on one side. So you're multiplying by like a minus b over a minus b. And the key thing is know your identities really well. Like the book says, know them inside out, upside down, and backward. They are the key. And that means you actually do need to memorize them.
That's the smartest thing I've ever heard anyone say about anything.
Okay, so let's cruise onward. So we're going to verify this identity. 1 minus tangent, quantity squared, equals secant squared plus 2 tangent negative x. First thing I want to do is get rid of the negative x. So I'm going to use the property right here that tangent of negative x equals negative tangent of x. So that means we have, well, and while we're doing that, why don't we just distribute this out too? So we know that a minus b quantity squared is a squared minus 2ab plus b squared. Now over here we have secant squared x. Now the minus x makes it a minus 2 tangent positive x. Okay, now the next thing that we want to do is use the substitution of secant squared and tangent squared. So we know that secant squared minus tangent squared equals 1. So what I could do is I could substitute for the, well, let's actually use this one. Tangent squared, now, okay, I think it's actually better to go this way. Secant squared equals tangent squared plus 1. We just add that over to the other side. So that's what I'm going to do. Here's a secant squared, and I'm going to make that a tangent squared plus 1. So I have 1 minus 2 tangent x plus tangent squared x equals tangent squared plus 1 minus 2 tangent x. Now you can see that we just have a rearrangement, or basically the commutative property of addition, that can make these things the same. Notice I have, let's just put the tangent squared over here. So if we just slide this over to here, then I've got tangent squared x plus 1 minus 2 tangent x equals tangent squared x plus 1 minus 2 tangent x. That's it. QED. Game over. Okay, so the key thing here was just knowing that tangent of negative x is negative tangent x, and then knowing that secant squared is tangent squared plus 1, and then everything works out. Okay, now, sine squared tangent squared equals tangent squared minus sine squared. Now notice I did away with the angles, so we're just going to deal with this notation. So what can I do here? Well, the thing that occurs to me is if I change the tangent into sine over cosine, then I'm going to have the same thing on both sides. So let's try that. So I go sine squared over 1 times, now tangent is sine squared over cosine squared. Now, tangent squared is sine squared over cosine squared minus sine squared over 1. All right, now, the key thing we need to do here is get common denominators. So, so I might as well just multiply the left out. So I have sine squared, or sine to the 4th, over cosine squared equals, now getting common denominators, the common denominator is going to be cosine squared. And so the sine squared stays the same. but I multiplied the bottom of this by cosine squared, so I better multiply the top by cosine squared. Okay, so now what we're trying to prove basically is that sine to the fourth equals sine squared minus sine squared cosine squared. So notice the left is nothing but sine on top, and the right has sine and cosine. So it makes sense to change the cosine into a sine. Okay, how do we do that? Well, we remember that sine squared plus cosine squared equals 1, which means cosine squared equals 1 minus sine squared. So I'm going to make that substitution. So sine to the fourth over cosine squared equals sine squared minus sine squared times 1 minus sine squared all over cosine squared. Notice all I did was change my cosine squared into a 1 minus sine squared. Okay, now if I distribute this out, notice I have sine to the fourth over cosine squared equals, now, sine squared minus sine squared times 1 is just sine squared. Now minus a minus sine squared times sine squared, which is a plus sine to the fourth all over cosine squared. Okay, so you can see now sine squared minus sine squared cancels, and I'm left with sine to the fourth over cosine squared equals sine to the fourth over cosine squared. That's it, QED. Okay, so notice two main tools that I used here is, first thing, I got rid of the tangent and made it in terms of sine and cosine. So now everything's in terms of sine and cosine. And the second thing I did was I got rid of the cosine squared, turned it into 1 minus sine squared. Now it's just algebra. Now we get the common denominator of the two fractions. We put it all together, we distribute, and the sine squareds cancel, and my left and my right match. So that's it. All right. Cosine over 1 plus secant equals 1 minus cosine over tangent squared. Now this is an example where the multiplying by the conjugate is going to help us. So if I multiply, I could multiply the top and the bottom here by 1 minus secant, or I could multiply the top and the bottom here by 1 plus cosine. So let's do the left side. So we have cosine over, let's do that again. Cosine over 1 plus secant times 1 minus secant over 1 minus secant. And I'm not touching the left, or I mean the right side. Okay, so now I multiply by the conjugate. Now the reason for that is because I have an a plus b times an a minus b that's going to give me an a squared minus b squared. Okay, so I have cosine times 1 minus secant on top over 1 plus secant times 1 minus secant, remember, is 1 squared minus secant squared. Now, let's see. Okay, next, I want to look at the secant squared because I have a tangent squared over on the other side. If okay, wait, let's cut this for a second. I think, okay, so when I distribute what's on top, notice what I'm going to have is cosine times 1 times cosine times secant. Now, cosine times secant is 1. So basically distributing this, I get cosine minus, well, let's just do this, cosine secant over 1 minus secant squared equals 1 minus cosine over tangent squared. Okay, now cosine times secant is 1, so this becomes cosine minus 1 over 1 minus secant squared. Now, okay, so we have cosine minus 1 over 1 minus secant squared. And on the right, we haven't touched that, the whole problem. Okay, so now what I want to do is, I know that secant squared minus tangent squared equals 1. So if I basically tangent squared equals secant squared minus 1. Okay, notice I have a 1 minus secant squared, and I want a secant squared minus 1. So I need to switch the subtraction. Now, when I switch the subtraction on the bottom, I switch the subtraction on the top also. So I'm basically multiplying by negative 1 over negative 1. And so that'll make 1 minus cosine over secant squared minus 1 equals 1 minus cosine over tangent squared. Now we have secant squared minus 1 equals tangent squared. So I have 1 minus cosine over tangent squared equals 1 minus cosine over tangent squared. That's it, QED, game over. Okay, the next problem, we have secant over sine minus sine over secant equals tangent squared plus cosine squared over tangent. Now, the thing to do is work on the left and the right side together. So if we want a common denominator on the left, then that common denominator is going to be sine times secant. So let's just do that. Sine times secant. Well, notice I multiplied the left by secant, so I better multiply the right by secant. And I multiplied the right by sine, so I better multiply the top by sine also. So now the next thing we can do is sine times secant equals sine times 1 over cosine, which equals sine over cosine equals tangent. So we can make this, the denominator becomes just tangent, just like up here. And then the other thing we want to do is change the secant squared and the sine squared. So what we're going to do is we're going to say that secant squared minus tangent squared equals 1. So that means secant squared equals tangent squared plus 1. So I'm going to make that substitution there. And then sine squared plus cosine squared equals 1. So that means sine squared equals 1 minus cosine squared. All right, so now I have all of my substitutions. So I'm going to substitute secant squared for tangent squared plus 1. So that just gives me tangent squared plus 1. Now, minus sine squared. So that's going to be minus 1 minus cosine squared. All over sine times secant, which we said is tangent. And I'm just going to recopy the right side. Okay, now, notice what I have here is tangent squared plus 1 minus 1 is just the 1's cancel, and I have minus a minus cosine squared. And everything works out happy. So, that's it, QED. Okay. Okay, so basically, notice what we did was we got the common denominators up here, and that gave us squared functions, and that's what we have up here is squared functions. And so the denominator sine secant turned out to be tangent, which matches the right. And then all we did was we used our two Pythagorean identities to change the squared functions into the other squared functions. So changing secant squared into tangent squared and changing sine squared into cosine squared. And when we did that, the 1's canceled and the sines all turned out right. So that's all happy. Now, one last thing we're going to do in this section, and that is show that a supposed identity is false. So basically, we want to disprove something. Now, in math, when you disprove something, you're basically just going to find a counterexample that shows it to be false. So, sine of A plus B equals sine of A plus sine of B. Now, that would be nice if it was true, but it really isn't. So, let's prove that it's not true. So, all we do is pick an A and a B that we know. So, let's just let A equal let's see, what can we let? Yeah, let's let A equal 90 degrees, and let B equal 45 degrees. Now the reason I pick these two numbers is because I know sine of 90 and I know sine of 45, and I also know sine of 90 plus 45, that's 135. So when I put those in, I have sine of 90 plus 45 is 135 equal sine of 90 plus sine of 45. Now remember, 135 is the second quadrant. So sine of 135 is a positive square root of 2 over 2. And on the other side, sine of 90, well, 90 is straight up, so sine of 90 is 1, and sine of 45 is square root of 2 over 2 also. So notice what we show is square root of 2 over 2 equals 1 plus square root of 2 over 2. So that is false. Now, there are plenty of different angles that you could choose to show that this is false, but the key thing with a counterexample is you just need to show one example that's false, and the whole statement's false. Okay, let's try another one. Cosine 2x equals 2 cosine x. So, what should we let x equal so that we know both sides? Well, what if we let x equal pi over 6? So, cosine of 2 times pi over 6, which is pi over 3, equals 2 cosine pi over 6. Well, what's cosine pi over 3? It's 1/2. And what's cosine pi over 6? Well, it's going to be square root of 3 over 2. So, 1/2 does not equal square root of 3. So once again, we have a contradiction which tells us that cosine 2x does not equal 2 cosine x. Okay, that's it. Have fun with these.
That's all, folks.